Alright guys, so today I'm going to talk about the hyperbola. To do that, I actually need to start with ellipses. So, what I have here is I've drawn a horizontal ellipse, and I've given you the equation of a horizontal ellipse. Now, a horizontal ellipse is x minus h squared over a squared plus y minus k squared over b squared equal to 1. A couple of things. The center is at h comma k, so this has been moved left or right h, and up or down k. A is always greater than B. Okay, and so if the larger number is under X, we get a horizontal ellipse. If the larger number flip-flops over here and is under Y, we would get a vertical ellipse. So it'd be longer in the vertical direction. It's always equal to 1. A squared minus B squared equals C squared. A is the semi-major axis. So the major axis is the width of the ellipse. The minor axis is the height of the ellipse in this case. A is half of that. It's from the center to the outside and from the center to the outside for B. C is the focal length. That is how we find the foci. Okay, the foci are these 2 points labeled with F's. Very important in an ellipse. And the eccentricity is defined as C over A. It's a ratio of the focal length to the major axis length. Semi-major axis length. Eccentricity for an ellipse is always between 0 and 1. An eccentricity of 0 actually gives you a circle. So if you take a circle and make it slightly eccentric, that makes it into an ellipse. And basically what you're doing is the focus of a circle is at the center. When you make this thing slightly elliptical, the two focus points would be very close to the center. And as we get more elliptical, the focus points, the foci, would be further and further from the center. Okay? Please note that if the larger number is under the x value, it's going to be a horizontal ellipse. If the larger number is under the y value, it is going to be a vertical ellipse. Okay, so you need to know all of that before we talk about the hyperbola. So now from there, what we're going to do is we're going to take the ellipse and we're going to make it more and more and more eccentric. And this is not really what happens, but it's kind of how my brain processes it. I'm going to take an ellipse and I'm going to make it more eccentric, more eccentric, and more eccentric. Move those focus points further and further and further and further and further and further from the center until they're almost as far away as I can get. And I'm literally going to turn this ellipse inside out so that now the foci have gone outside of the shape. And that is when you get a hyperbola. So how is a hyperbola different from an ellipse? Well, it is wildly different from an ellipse. So I'm going to show you a picture here. This is what a hyperbola looks like. I'm going to go through this whole picture with you. First thing to know is in a hyperbola, C will be greater than A. Why? Because the focus will be outside. So this is the inside of the hyperbola. The focus is outside of the hyperbola. A is still the semi-major axis, defined from the center to the vertex of the hyperbola. B is still the semi-minor axis, defined from the center to the outside of the inner box. C is still the focal length. It's where your focus is going to be. You're going to have two of those, two foci, one on the right, one on the left. Okay, I'll label that one as well. Okay, eccentricity for a hyperbola is always greater than 1. So for an ellipse, it is less than 1. For a hyperbola, it is greater than 1 because you've turned this thing inside out, and this axis is now longer than this axis, giving us an eccentricity of greater than 1. And I don't think I wrote it on the page here, but E for hyperbola is still defined as C over A. Still defined as C over A, but because the C axis is longer than the A axis, you get an eccentricity greater than 1. And in this case, C squared is A squared plus B squared. It actually fits Pythagorean's theorem, but we don't call it that because it's not Pythagorean's theorem in a hyperbola, even though it's the same formula. A and B create the inner box, okay? And so you've got this imaginary box. If you plot a hyperbola on graphing software, you're not going to see this, but you have this imaginary inner box. So you're going to go from the center of the hyperbola over A units right, over A units left, up B units, and down B units. And you're going to make this imaginary box. And I've drawn it as a dashed line. Through the corners of these the corners of this box, you're going to draw asymptotes. So these lines here are actually asymptotes. Okay? And then at the vertex, which is A from the center, you're going to follow your asymptote, and you get your hyperbola. The hyperbola is, in fact, an asymptotic function. Okay? Vertex is always on the major axis, and the curve follows the asymptotes. One interesting thing about hyperbolas, in an ellipse, the major axis is always larger. A has to be bigger than B. This is not true for a hyperbola. Okay? So, and I'll show you the difference. So this particular hyperbola here is a horizontal hyperbola because it is in the form of x minus y. So x minus y is going to give us a horizontal hyperbola. Okay? If I find a tiny little space here on my paper to write it, if I wrote y minus k squared over, and it doesn't matter a squared or b squared, minus x minus h squared over b squared equals 1. This would be a vertical. Okay? And it would be vertical because it is in the form of y minus x. Y minus x. Okay?